So yes, quest due Wednesday, quiz Thursday, right? And what we've been talking about is how work, power, and energy actually applies to rotational motion as well. And so we said that we have rotational energy, 1/2 I omega squared. We have rotational work, which is tau, change in our angle. Okay, so how much we're spinning. Okay. Reminder that this is the angle of how much we have turned, not the angle of the ramp that we're on. Okay, so those could be referring to two different angles. Okay. That this is rotational speed, and what is I based on? The moment of inertia. What is it based off of? Yeah, the shape, right? So if it's a cylinder, if it's a sphere, or if it's a donut, or sometimes it'll be an odd shape and they'll have a solve for it. Okay? So this is similar to a problem I've seen multiple times on AP tests. A solid cylinder mass M and radius R rolls without slipping down an inclined plane of height h and length L, whose incline angle with a horizontal is theta. So they're assigning this theta. Determine the linear speed of the cylinder's center of mass when it reaches the bottom of the incline. Assume that is started from rest at the top. Okay. So we're starting with mass M, radius R. We're rolling without slipping. Did they tell us what kind of shape we have? Okay. So we know that we have, yes, I equals cylinder 1/2. And I'm going to go ahead and use capital M and capital R squared because we're given mass with radius rolls. Okay. And we're looking for what kind of quantity at the bottom? Velocity. What kind of velocity?
Linear.
Okay, so we need the linear speed. That's v typically, right? So how do we find that?
We can do
angular velocity.
Yeah, angular velocity times radius.
Angular velocity times radius. Okay, we will need that. Angular velocity. That's omega, right?
Yeah.
Times radius. R omega is equal to v.
There's also velocity final squared equals velocity initial squared plus 2ax.
We have kinematics. So vf squared equals vi squared plus 2ax. What else might you use? Let's just jot things down. We can brainstorm.
I don't know. F equals ma.
F equals ma.
Yeah.
Might as well when we're brainstorming.
Should we use
Torque.
So in that sense, yeah.
What's torque? Which one? Torque?
FR. Yeah, FR.
Just FR?
which is it?
No, FR sin data.
No, just FR, which then FR would be FG sin theta. And then also torque equals force times radius.
Oh, yeah.
Oh, torque could also be I alpha.
True.
That's true. Okay. What if we said it was easier than this? What if we've been overthinking all of our problems ever?
Alright.
What's the topic?
Kinematics. Oh, energy.
Energy. We're out of kinematics. Energy. What kind of energy do you have to begin with?
Kinetic energy.
Kinetic.
To begin with?
Potential.
You have potential. What kind of potential energy?
Gravitational.
Gravitation.
Okay. So at the very top, we have energy, and energy doesn't change. So energy, the total energy, or total mechanical energy, is equal to the total mechanical energy. And we said that the only energy we ever had to worry about at the top was potential energy, which we say U, G, is the only energy we have at top. If we had kinetic energy, it's not moving, it's not rolling, it's not on a spring. We don't have to worry about any of those. All of those are zero. What energy are we worried about at the bottom to determine linear speed? Okay. Here's the problem. is it just one type of kinetic energy at the bottom?
No.
No. It's linear, which is tangential, okay? And then it's rotational. Okay?
Plus, or they're both equal?
Yeah, it's the conservation of energy, so they'll add together. Good. It is a plus. And then that just means that all we have to do is label our things. We've got M, G, H. And we have K translational being 1/2 mv squared. And K rotational being
Plus 1/2 m omega.
1/2 I omega squared. Yeah, I. And we already know what to plug in for I to get it to m's. And we already know what to plug into velocity to get to, yeah, to get to v's. Okay, so and we're looking for this v, right? 1/2 mr squared. Most of the time, by the way. Wait. Omega is v over r. And that gets squared as well. Remember what we always come up against? What happens a lot of times? What cancels? The r's cancel. A lot of times your r's cancel. This is 1/2 big M v squared plus 1/4 m v squared. What was the question? Would the m's cancel out? Yeah. Oh yeah, you're not wrong on saying that. I was going to talk about it before the m's cancel, so I'm going to go ahead and say mgh right here. What we're trying to say is that our potential energy right here is converting into the two different types of energy, and you'll see that 1/2 mv squared is taken out as translational and how it's moving side to side, but it also uses some of the energy for rotational. Okay, so it's going to go into the fact that some of the energy is used just to rotate and spin this object. That's all it is. Yeah. It'd actually be going slower than a frictionless object, right? We could do all the friction stuff that we talked about before, and how it's slipping or not slipping in this case. And it would actually, in the end, be going slower because that if it's just translational, if all this was a block on a frictionless ramp, this would all turn into translational and it'll be sliding faster and faster. Okay. So yeah, after all is said and done, we end up with what we need, which is 4/3 GH square rooted, right? Equals V. That wasn't bad at all. Okay. There's more hidden algebra that I skipped over. Sorry about that. But y'all are strong enough in algebra to have rearranged in one step, I think, these days. Okay.